All right, welcome to the homework help for Unit 1, Lesson 9, Geometric Meanies. Here we go. All right, the first question that we're going to tackle was not number 1 or number 2. I believe it's on actually the second page, so let's go look at that. That is 2 continued, and it is number 4. There we go. Okay, so it's a little tricky since it's on the bottom of this page, but we're going to be working on the next page. So we'll zoom out a little bit, and hopefully this works out. Let's see, can we still see it, or is my video going to get in the way? Oh, hang on, don't need a note here. Let's see. All right, there we go. We can still see here. All right, so arithmetic sequence. So we have arithmetic in one column, geometric in the other, up where our table is. So let's just tackle the arithmetic sequence first. So we know that this is going to have the same step each time. So if n equals 1, well, we would plug that in and say that, okay, we plug in 1, that means that, oh, this minus 10 portion over here, right, the minus 10 portion here, oh, I don't think it drew for me. Oh, it did a little bit. All right, so this minus 10 portion here, right, if we plug in a 1, that's going to go away, right? And plus we know that 100 is our starting value. So our starting value for arithmetic was, come on, here we go, was 100. Right, that was our starting value. And then it says for our arithmetic sequence that we are just taking away 10 each time. So 100 then becomes 90, and then 80, and then 70, and then 60. Right? We could evaluate, you could plug in 1 for n and find it's 100, 2 for n and find it's 90, 3 for n, and so on. But the shortcut is to know what happens step by step. So we actually don't have to revisit our equation because we know that the step each time is minus 10, minus 10, minus 10. Now let's look at geometric. We will do that in purple. All right, so we have a starting value of 1, it says. Starting value of 1. Well, we'll see. If we plug in a 1 for n, we should have 1 times 3 to the 1, which is just 3. So our starting value is going to be a 3. And it did not write that for me. That's okay. We'll go back. We'll try again. All right. So our starting value is going to be 3. And then what happens each time? It looks like, well, each time, since 3 is in the parentheses, that's our common ratio, we're going to multiply by 3 each time. So after 3, if we multiply by 3, we're going to get 9. If we multiply 9 by 3, we're going to get 27. Oh, not a new note again. Delete that. All right, we're going to get 27. If we multiply that by 3, we should get 81. And if we multiply 81 by 3, we will get 243. So there we are with our first question done. That is number 4. All right, on to the next one. We have number 6. Oh, another one where it is at the bottom of the page on one side and the top of the page on the other. So considering arithmetic and geometric sequences, would there ever be a time that a geometric sequence does not outgrow an arithmetic sequence in the long run as the number of terms in the sequence becomes really large? Explain. Okay, so we know that geometric sequences are like repeated multiplication, and we know that arithmetic sequences are repeated addition. So well, actually, is there ever a time that a geometric sequence does not get bigger and bigger and bigger than an arithmetic sequence? Well, let's assume that they have the same start point, but it doesn't actually matter. Like mathematically, like even with different start points, one could always outgrow the other. But it's asking, would there ever be a time that a geometric sequence does not outgrow? And yes, if the geometric sequence isn't getting bigger and bigger and bigger each time, but if it's actually getting smaller and smaller and smaller, like instead of doubling each time, what if it was getting cut in half? Right? If it's getting cut in half, right, if you're multiplying by a fraction, then it'll just get smaller and smaller, and if you're, adding a really small number, like your arithmetic could be getting bigger by, let's say, 1/10 each time. But if you're multiplying your number by 1/10 each time, that's getting much, much smaller. So one is increasing slowly, the other one is, I would say, decreasing rather drastically. So yes, it asked, considering would there ever be a time? Yes, right? Answer is going to be yes. If the common ratio, oh, didn't mean for that last little bit. There we go. If the common ratio is less than 1. Less than 1, right? Which means that the geometric, no, not a new note again, wow. Which means that the entire thing is decreasing. Oh my goodness, all of these notes. Decrease. I cannot get this to work without the notes, huh? Decreasing. There we go. All right, on to number 7. Each of the given tables represents a geometric sequence. Find the missing terms in the sequence and create the explicit and recursive equations. Show your method. All right, so we know that each one is geometric, right? Let's underline that. Each one's a geometric sequence. Find the missing terms and create the explicit and recursive equations. All right, we can do that. So our first step is to know, all right, if we're in a geometric sequence, that means that our steps are a common ratio. So whatever happens from 5 to this missing value also happens from 5 to 20. Okay, I didn't think it was going to turn off this time, but it did, and now it's back on, so that's good. All right, so whatever happens from 5 to the second term then happens again, and it becomes 20. So, well, what is it that happens over the entire jump? Well, I'd say the entire jump is a times 4, right? Right, we're multiplying by 4 because we're going to be talking about multiplication here since it's a geometric sequence. So there's going to be multiplication, right? The ratio from the first to the third is times 4, but that's 2 smaller jumps. So what 2 smaller jumps, right, multiplying will give us a times 4. And that's actually going to be we can talk about exponents, but that's, if we recall, 2 squared is the same as 4. So we can actually break this up into 2 little times 2 jumps, right? A times 2 and another times 2. So if we go 5 times 2, that's going to give us 10. And then 10 times 2 will give us 20. All right. So let's write our explicit equation here. So we're going to start with f of n equals, and our starting value is 5. And then we're going to multiply that 5 by 2 to the n minus 1. 2 to the n. Nope, don't want text here either. Oh my goodness. All right, 2 to the n minus 1. There we go. So that's our explicit equation. And now our recursive, right? F of n equals the previous f of n minus 1. And then what are we doing each time? We're just multiplying by 2. So multiply by 2. There we go. And we're on to the next one. What is the next one? It looks like it's 9. Oh, and 9 goes to the bottom of the page and starts up again at the top of the next one. So we'll just go up here. Aha, here we go. There's number 9. So we're doing the same thing here. We have to fill in the blanks, and we know it is still geometric. So it's still geometric. So what happens on this jump? And that is just not at all what I drew, but that's okay. We'll erase it. We'll try again. Right? What is the jump that happens here? Well, 108 divided by 3. We're trying to figure out what this factor is. From 3 to 108 is saying like, oh, 3 times what equals 108, right? Because we want to figure out what the jump is. And the way that we'll figure that out is say, okay, well, let's just divide the 3 by both sides, right? Since it's a factor, we can just divide both sides by 3, divide by 3, and we end up with blank equals 36. We can do that on the calculator, but I just happen to know, right? It happens to be 36. So 36. So this whole jump here is times 36. And since this is 2 jumps, we're looking for a perfect square, right? We're looking for what squared becomes 36. And we might recognize that 6 squared, oh, it did not right there. 6 squared is equal to 36, which means that each of our little jumps is now times 6, right? So that's times 6, that's another times 6, and finally to the 4th term, that should be times 6. So let's take a look at this first jump from 3 to something, and from something to 108. So what is 3 times 6? If you said 18, you got it. And now, this one looks a little bit harder. 108 times 6. We might be able to do this in our head, but it's good practice to do it out as well. So let's go 108 over on the right side. Let's do 108 times 6. All right, we start out with 6 times 8 is 48. So the 8 comes down and we bring the 4 up. 6 times 0, well, that's going to be nothing, right? 6 times 0 is 0. We bring the 4 right down, so that's good. The 4 comes down. And then 6 times 1 is just 6. So we have 648. All right, so we can write that down, 648. There we go. So we've filled in our table. Now let's move on. Okay, we need an explicit equation. Let's do that. We'll do that in green, right? We like doing green. So we have the explicit equation, f of n equals, what was our starting value? What was our starting value? Let's look up here. It was 3, right? So our starting value is 3. And then we multiplied that by, what was our common ratio was 6 to the n minus 1, right? That's what we've gotten in the practice of doing. Or, right, I'll say or, because we can write this 2 different ways. Another way we can write it is f of n. Oh, hang on. It does not always like when I try to write the parentheses, huh? F of n equals, and now instead of 3 times 6 to the n minus 1, what we can do is we can actually say 1/2 times 6 to the n. Right, and that sort of like takes the n minus 1 portion and combines it with the 3 and just makes it so that we only have n in the exponent. So that can also be helpful, but these are equally correct answers. All right, and now the recursive equation, f of n equals, so our current equals our previous, f of n minus 1. And what are we doing each time? We are multiplying by 6, so times 6. And then we need to note that the first term we had was 3. So there we go. Put a little comma. Those are 2 different equations. There we go. So that is our recursive form of this equation. All right, number 10 is down here, but I don't think we're doing number 10. Instructions for the go. Use the given information to write the explicit equation for each geometric sequence. All right, so we're writing explicit. Write the explicit equation, and we know that it's a geometric sequence. All right, that's all we need to do. Write an explicit equation for a geometric sequence. So let's go over to the next page and see. We just have to do 11, and then we're done. So just number 11. All right, so we know that the first number is going to be 13. All right, so f of 1 is 13, and the common ratio is 4. Okay, so from that, right, I'd say, oh, we're doing an explicit. So our starting value, or our first value, is 13. All right, so we're going to start with a 13 right here. Then our common ratio is 4, so we're going to put 4 in parentheses. And then we're going to put up here, we're going to put n minus 1. N minus 1 goes up there. And I think that should work. Let's see. The common ratio is definitely 4. We're definitely going to multiply by 4 each time n goes up. And then are we always going to have 13? If we plug in 1 for n, this becomes a 0. 4 to the 0 becomes 1, and we're just left with 13. Okay, so that's perfect. So it's f of n equals 13 times 4 to the n minus 1. That is our explicit equation for this geometric sequence. And then we have nothing left to do here. Let's zoom out just to make sure. Yep, that is the end. All right, perfect. That is the end of this homework help.